Deep within a Japanese mountain pass lies a 43-kilometer magnetic levitation train track, a rare piece of technology poised to become part of the world's first intercity maglev line connecting Tokyo and Osaka. This allows them to operate in any weather and reduces maintenance costs due to minimal friction and fewer moving parts. Despite these advantages, the only commercial high-speed maglev line currently operates over a mere 30 kilometers, linking Shanghai's airport to its city center in just 8 minutes. However, this short distance undermines the maglev's potential, as the train barely reaches top speed before slowing down, averaging 225 kilometers per hour slower than conventional high-speed rails peak. The planned maglev network spans just 400 kilometers, dwarfed by the 60,000 kilometers of global high-speed rail tracks, with another 50,000 under construction. Why is maglev deployment so limited? Let's explore how these trains function and why their use remains restricted. Maglev trains levitate using two primary methods: attractive forces that pull the train upward or repulsive forces that push it up. The gap between the rail and magnet, typically 8 to 12 millimeters, is critical, as the attractive force weakens with the square of the distance. This requires active control systems and feedback loops to maintain stability, as any drop in the train could weaken the magnetic force, causing further descent and inherently unstable setup. Japan's maglev system, however, uses a different approach, achieving a 10-centimeter gap 8 times larger than electromagnetic suspension and a passively stable levitation method, ideal for an earthquake-prone region. Here, magnets on the train interact with passive coils on the track. As the train moves, it induces a changing magnetic field in the coils, generating an opposing field that lifts the train. This electrodynamic system only works at high speeds, requiring wheels for low-speed operation that retract into the carriage above 100 kilometers per hour. The track's coils are arranged in a figure-8 pattern with north and south poles aligned vertically on either side. If the train shifts slightly, the magnets induce currents in the opposing coils, creating a stronger magnetic field that nudges the train back to the center, maintaining stability without complex controls. Japan's LO maglev, the first of its kind, relies on superconducting coils to generate powerful magnetic fields. These niobium-titanium coils, cooled by liquid helium and housed in liquid nitrogen containers, must remain below their critical temperature to conduct electricity without resistance. In a closed tube, a standing wave creates regions of high pressure and temperature at the ends and cooler areas in the center. A stack spanning these regions, paired with heat exchangers, transfers heat away from the coils, maintaining their superconducting state. Each train car has 8 coils, 4 per side, generating intense magnetic fields that could pose risks to passengers and nearby objects. To address this, engineers use electric steel shielding to redirect magnetic fields away from the passenger cabin and stations. Electric steel, with 3% silicon and large, aligned crystal grains from cold rolling, has low reluctance, allowing it to carry 30% more magnetic flux in a specific direction. This diverts the field effectively, though the heavy shielding is used sparingly. The magnetic field is further tailored by arranging the coils to create a low-field bubble in the cabin. By aligning 4 sets of coils on each side with alternating north and south poles, the field strength in the passenger area is reduced to 0.5 millitesla, comparable to Earth's magnetic field. Near the magnets, however, the field remains strong, requiring tracks to be made from low magnetic steel or fiber-reinforced composites to avoid interference. Propelling a levitating train presents another challenge, as there's no ground contact for traction. Conventional trains use electric motors to turn wheels, but maglevs employ linear motors. These consist of alternating coils along the track that attract and repel the train with precise timing, pushing it forward. Braking reverses this process, using regenerative braking to recapture energy. At low speeds where electrodynamic systems are less effective, trains rely on wheel brakes and air brakes for rapid deceleration at high speeds. Power delivery is also complex. Lower speed maglevs use a low-friction third rail, but at high speeds, Japan's system uses linear induction coils to harvest electricity from the track's changing magnetic fields, creating some magnetic drag but eliminating the need for onboard generators. Japan's Maglev line, set to be the first long-distance high-speed Maglev, will cover 285 kilometers from Tokyo to Nagoya by 2027, with the remaining 438 kilometers to Osaka completed a decade later. Japan has long led in rail innovation, launching the world's first high-speed Shinkansen line in 1964, connecting Tokyo and Osaka. By the 1970s, they were testing Maglev prototypes on a 7-kilometer track in Miyazaki, achieving 60 kilometers per hour in 1972 and 411 kilometers per hour by 1975. As testing outgrew this track, the 20-kilometer Yamanashi test track was built in 1990, along the planned Tokyo-Nagoya route. This track helped refine the LO Maglev, capable of carrying 700 passengers across 12 cars at 500 kilometers per hour. Beyond engineering, Maglevs face economic hurdles. They compete with cars, planes, and conventional trains. For example, between San Francisco and Los Angeles, trains outperform planes when factoring in airport distances and security delays. A high-speed train saving 2 hours for 900 passengers equates to 1,800 hours saved, boosting productivity. Cities 200 to 800 kilometers apart, like Washington, D.C. to New York, are ideal for high-speed rail, potentially cutting travel to 60 minutes. However, Maglevs require entirely new tracks with electromagnetic coils and specialized materials, making them 10 to 50 times costlier than high-speed rail. The Tokyo-Nagoya Maglev line's cost has risen to $13.7 billion, or $77 million per kilometer, compared to $2 million per kilometer for France's TGV network in the 1980s and 1990s. Even against Japan's existing Tokyo-Osaka high-speed rail, the Maglev costs 11.3 times more per kilometer, a steep price for a 1-hour time reduction. The Tokyo-Nagoya line's route, with 86% underground to navigate mountainous terrain, further escalates costs. Tunneling over 200 kilometers increases construction expenses, and tunnels create operational challenges. At 500 kilometers per hour in open air, air moves aside, but in tunnels, trapped air increases drag, raising energy consumption by 30% compared to the existing Tokyo-Osaka line. Still, Maglevs remain more energy efficient than air travel. In the U.S., where high-speed rail is underdeveloped, Maglevs face even greater barriers. Areas like the Texas Triangle, with 4 major cities connected only by highways, are ideal for rail, yet investment lags. Maglevs, with their high costs, seem impractical for widespread adoption beyond niche projects. Recent speculation about room-temperature superconductors has renewed interest in Maglevs, as they could simplify construction by eliminating complex cooling systems. Magnetic fields are central to many technologies, and understanding them is a valuable skill. For those interested in learning more, Brilliant offers a free course on magnetism and electricity accessible via brilliant.org/real-engineering. Their interactive platform includes courses on AI, data science, neural networks, and a partnered real engineering course. The first 500 users signing up through the link get 20% off Brilliant's annual premium subscription, providing access to thousands of lessons, including a new course on probability for practical decision-making.